Welcome to myprojectbazaar.com. Today we discuss about the process unsupervised deep learning applied to breast density segmentation and mammographic risk scoring. Let me see the abstract of the process. Identification of defects using mammogram images helps in saving life of many women. Mammogram segmentation usually involves classifying mammograms into several regions, including the breast region and the pectoral muscle. The principal feature of a mammogram is the breast border, otherwise known as the skin-air interface or the breast boundary. Due to the nature of X-ray, each pixel in the mammogram represents two or more tissues. Superimposition of different tissues types makes it difficult to differentiate between different regions. The classification method helps to solve this problem by differentiating the different regions in the images more accurately. Using mammogram, the presence of the dense fatty tissue in breast regions can be identified. The input mammogram images were resized and they were converted into grayscale. The input image is divided into small patches of fixed size. Sparse auto encoding process is employed for the extraction of the features in the images. The process of transformation is applied to the values obtained from each patches. Encoding and decoding were employed for the extraction of the features. In the proposed system, the dense fatty tissues were identified with the help of the extraction of features based on sparse autoencoder. The extracted features were classified using convolutional neural network in order to identify the different regions in the mammogram images. The convolutional neural network consists of two-layer neural network is selected, the convolutional layer and the multinomial logistic regression layer. The convolutional neural network separates the input image into four different layers, indicating different regions of the images. The predictions for each patches were fused, resulting in final segmented image. From the segmented regions, the dense fatty tissue percentage is identified. The performance of the process is measured with the help of performance metrics like area under curve, dice coefficient, and percentage mammographic density. Let me see the flow of the process. Input mammogram images were resized and they were converted into grayscale. The images were divided into patches of fixed size and they were used for the extraction of the features. The feature extraction process is divided into feature learning step and the feature encoding step. Sparse autoencoding process is employed for the extraction of the features in the images. In sparse autoencoding process, features learning is the first step. The mammogram image patches were encoded. The autoencoder consists of three or more layers: an input layer, some number of hidden layers, which forms the encoding process, and an output layer whose units corresponds to the input layer. A sparse autoencoder has a very few neurons that are active. The neurons in an artificial neural network is uniformly considered as active if its output value is close to 1, and while it is considered inactive if its output value is close to 0. The features obtained from each patch are then used for the feature encoding process. In the feature encoding process, the process of transformation is applied to the values obtained from each pixels. Encoding and decoding processes were employed for the extraction of the features. The process of encoding is a minimized solution for the function. This function were defined for the encoding and decoding processor. The sparsity term is included in the encoding processor. Finally, these features were then classified using serial classifier into these different regions. The classification process. The convolutional neural network consisting of two-layer neural network is selected for the proposed classification process. The convolutional layer and the multinomial logistic regression layer. The weights and the bias terms were fine-tuned. The three class labels were mainly used for this process: pectoral muscle, background, fatty tissue, and the dense tissue. The threshold ranges for different regions in the images were identified based on the input image pixels. The image pixels that satisfy the threshold ranges were assigned the particular label. The prediction for each patches were predicted values for each patches were fused, resulting in a final segmented image. From the different regions identified, we measure the percentage of the each regions that we have segmented. From this percentage, the density calculation is done and the overall percentage is measured. The performance of the process is measured with the help with the classified result of the CNN classifier in terms of performance metrics like area under curve and the uh, pro- and the dice coefficient values obtained for the segmentation processor. So this performance matrix is calculated based on the result final obtained result in the ground truth value comparison. Let me see the running procedure of the process. If you want to run the code, select the file main.m which is present in the source code folder. Right click it and click on run file. You will get the process started. First, we have to select any one of the input images which is present in the dataset. The dataset consists of benign and the malignant tumor portions. So we select any one of the dataset and we select the input image. The process goes. This is the input image that we have selected. For this input image, we applied the autoencoder feature extraction, sparse autoencoder feature extraction process. So from that we have obtained these optimal conditions and the functional values. Based on these, the extracted features were obtained from the input image. This is the features extracted from the input image. This consists of the features has been extracted for each 3x3 patches of the input image, and for each pixels the obtained feature values were displayed here in the table format. From these extracted patch features values, we classify whether the particular patch is belonging to which portion. So the convolutional neural network is used for this process. This is the segmentation result obtained using the convolutional neural network. So the each patches were divided into the classified into several regions. So as we can see, the pectoral muscles, normal tissues, fatty tissues, and the other regions were segmented separately. From this, we can measure the percentage of the tissues ratios in each of the regions. This is the density scoring obtained for the pectoral muscles regions, fatty tissues, and the dense tissues value. After that, we measure the performance of the process with the help of area under curve dice coefficient. So this is the performance values that we have obtained. So from the performance values that we have obtained, we can see that the proposed approach segments the image in a more accurate manner. Finally, we have acquired the dense tissue percentage from the obtained density scoring. Thus, we have clustered the input mammogram image into different regions, and we have measured the density of several regions. The performance of the processes were measured, which indicates that the proposed approach is more enhanced. Thank you.